All right, so in this video, we want to sketch out this rational function over here. So we want to do the entire curve sketching algorithm. So what we notice is we have a cubic equation divided by a quadratic equation. So the first thing we want to do is just factor that cubic equation. I'll do that on the side because I don't want to do it in the whole equation. It takes too much space. So if I try and group this, it won't work because I won't get a common factor on each side. So I have to do factor theorem here and synthetic division. I'll start by taking multiples of this number over here. So f of 1 and f of 2. I'll start with those two, see if any of those are a factor. I'll just sub these into my calculator. Then negative 48 for this one. And if I try positive 2, I get negative 50, so those don't work. I'll try positive 3 and positive 4 next. If these don't work, I'll go to negative numbers. I personally like to try the positive ones first. Negative 36, and f of 4 is 0. So I found my first factor, which is x minus 4. I'm going to divide this using synthetic division. So 4, 1, 2, negative 15, negative 36. If you don't know how to do synthetic division, you can just do long division. You should end up with the same answer as me. So 1, 4, 6, 24, 9, 36, 0. So I can write this in factored form now as x minus 4. That's from the factor there. And these are the coefficients of my equation, x squared plus 6x plus 9. And now I can factor this trinomial. It's just a perfect square, or you can do your man method. It's just x plus 3 squared. So here on the top, I have x minus 4 times x plus 3 squared. And on the bottom, I can common factor out a 5. X squared minus x minus 2. And now I can factor this trinomial using my man method. That's just x minus 4, x plus 3 squared over 5 times x plus 1 and x minus 2. Okay, so now that it's fully factored, I can start doing all my key information. I'll start with the vertical asymptotes. Nothing can cancel out here, so there's no holes. Vertical asymptotes are solutions to my denominator, which is negative 1 and positive 2. There's no horizontal asymptote because the degree on the top is greater than the degree on the bottom. X-intercepts are just my solutions to my numerator, which are positive 4 and negative 3. For the y-intercept, I can just sub in 0 into these equations, doesn't matter which one. Just use the first one because all of this is 0. So I have negative 36 divided by negative 10, which is basically 3.6. Now I need to find the equation of my oblique asymptote. And to do that, I'm going to do long division. So I want to divide this by this. I'll do it on the side over here. 5x squared minus 5x minus 10. And here I have x cubed plus 2x squared minus 15x minus 36. Now, there are multiple ways to do this long division. It's a tough one. Some people choose to remove the 5 and just do the long division and then divide by 5 in the end, which could possibly work as well. But I'm just going to do it like this with either fractions or decimals. Doesn't matter which way you want to do it. So x cubed divided by 5x squared is 1 over 5x. Going to multiply 1 over 5x with this entire equation. So I will get x cubed minus x squared minus 2x. I'll do my subtractions. X cubed minus x cubed is 0. 2x squared minus negative x squared is 3x squared. Negative 15x minus negative 2x is negative 13x. I'll bring down the negative 36. So now I'm going to do 3x squared divided by 5x squared. That's just plus 3 over 5. Going to multiply 3 over 5 with this full equation and subtract it. So 3 over 5 times 5x squared is just 3x squared. 3 over 5 times negative 5x is just negative 3x. And 3 over 5 times negative 10 is negative 6. Subtract these two. 3x minus 3x is 0. Negative 13x minus negative 3x is negative 10x. And negative 36 minus negative 6 is negative 30. We don't care about the remainder when we do long division here. We only care about the equation on the top. So the equation of our oblique asymptote is y equals 1 over 5x plus 3 over 5. Now, with all this information given, we can do our sketch. On my sketch, I always start with my vertical asymptotes and my intercepts. The vertical asymptote at x equals negative 1. And another vertical asymptote at x equals positive 2. And then I have x-intercepts at positive 4, negative 3. And I have a y-intercept at positive 3.6. I'll label the points after I do the drawing. I also have an oblique asymptote that looks like this, 1 over 5x plus 3 over 5. So 1 over 5 is a really, really narrow slope. And 3.5 would be the y-intercept, which would be here. So the oblique asymptote would look something like this, but you only want to draw it for the outsides, not for the insides. I'm going to draw my oblique asymptote. This is a bit approximate. So pretend like it's coming through here. It's going to hit 3 over 5 as my intercept, and then it's going to keep going on that side. I think I should have drawn this a bit more narrow, just like that. Yeah, the point is not really the best, but the drawing, I guess, it's going to be a bit difficult to draw it, but we'll try it. So now I need to figure out what my graphs look like. I know I have a point over here. If I want to start on the right side, for example, I want to draw this area here. I'll do f of 2.01. So if I put 2.01 in my main equation or in factor 1, doesn't matter, whatever's easier. We'll do that in my calculator. I get a large negative value. So if I get a large negative value, it means it's on the bottom over here. And the graph is just going to look like this on this side. can label this point over here, which is positive 4. Now let's test out the center range over here. The center range, I want to test a value really close to -1 first, but slightly smaller, basically on the right side of this. So I'm going to do f of -0.99. Put that in my calculator. Just give me a sec. Oops, I accidentally put 1.99 first, which was, okay, we'll do that one first. I just did that in my calculator. I did f of 1.99, which is basically really close, but on the left side over here. I accidentally tested this one first in my calculator. Don't know why. Again, I got a large negative number, which means that this is on the bottom over here. And let me test -0.99 next. Oh wait, I just realized I've been putting these in a wrong equation. I forgot to enter the denominator. So this one is not correct. That one's good over there. I still have to do the denominator for this one. So ignore this calculation. Okay, this is actually positive, not negative. Only did half the calculation. I only put in the top half of the formula by accident. So this point is actually not in the bottom. This one is on the top. If I test my next point, which is -0.99, I'll just sub that into my equation again. And make sure you sub it in the full equation. Don't make the silly mistake I just did by subbing it in just the top. And I get a large positive number again. So this means this is all the way on the top. Now you don't know if this is actually the minimum or not. You can't prove that except in a calculus course, so you don't have to worry about that. You can just draw it like this. It's perfectly fine. Don't have to actually find the value of the minimum or where the minimum is. So again, that's meant for calculus. We can label our y-intercept now, which is 3.6. And last, let's do the left side over here, which I didn't have really enough space. That's why I left it for last. Normally I would start on the left side. Let's use this line over here, which I've drawn above. This one is a bit too steep, I think. The slope should be 1/5. So this line should be like really, really narrow, basically. We have a point over here, which is -3. So the first thing I'm going to do is I'm going to test a point right here next to -1, but just on the left of it. So I'm going to test f of -1.01. I'll sub that in my full equation again. And I get a large negative value. So if I get a large negative value, it means this is on the bottom. And then these two definitely connect like this. And this part is a bit tricky now to draw because there's two possibilities that can happen. The graph can turn back and go above the asymptote, or the graph can turn back and go below the asymptote. Obviously, the asymptote is not drawn perfectly for it to go below. or above. So the really challenging part in this question is to figure out whether this graph is going to be above or below the asymptote. Okay, I think the only way to do this is to sub in a point over here, for example, -10. I'm going to sub in -10 into the original equation. And I'll do that on my calculator. I get -1.27. The value is really important here. You can't just write large negative or large positive with some oblique asymptotes. So if I do f of -10, I get -1.27. Now I'm going to put -10 in my oblique asymptote. So if I put -10 in my oblique asymptote, I'll call that g of -10. Again, I'll do this in my calculator. So 105 times -10 plus 3/5. I get -1.4. So according to this calculation right here, you can tell that the oblique asymptote is actually below, because this value is lower than this one. -1.4 is lower than -1.27. This means that when this deflects over here, it's going to just hug the asymptote from above, because the oblique asymptote, with this calculation, I've proven that the oblique asymptote is below the actual function itself by a very small amount. And we can finally label this point over here, which is -3. It's going to be a bit more smooth, but as you can tell, like I said, it's above the oblique asymptote, not below. Very important to do this calculation to verify that. Otherwise, it's impossible to really tell.